And now we have second speaker. Yeah. Yeah, so we have our next speaker, Anupama Roy from ISR Mohali, and she is going to talk about something extreme events. And
So, good afternoon, everyone. So, I'd like to thank the organizer for giving me this opportunity to talk here. So, today I'm going to talk about.
The mic is working, right?
Yeah, it's working. I think. It's working. It's not. Okay. No, it's not working. Hello. So,
yes, it's working.
it's very difficult.
Okay.
No, I have. Okay. So this work has been done with Professor Sudeshna Sinha, and recently it has been accepted for publication in Chaos. So now this is the sort of outline of my talk. So I'll give a brief introduction, brief introduction on extreme event. Then I'll explain the model, and then I'll show you the result for extreme event on the single neuronal map, and then I'll show you result for the extreme event on coupled neuronal map and summarize my talk. So many natural system actually exhibit large impact event recurrently. So, and sometimes these events actually can have catastrophic consequences. For example, recent flood in Delhi, there actually the water level of Jamuna goes high, and there are also other events like epilepsy in brain. So there actually neuron starts firing and synchronously. So an extreme event is one where the variable actually was a variable of a system exhibit large excursion to the values which are actually far from the mean. So and these values are actually recurrent, aperiodic and rare in nature. So there are many works to understand the mechanism behind this extreme event. It has been studied for many systems like coupled chaotic oscillators, stochastic system, many deterministic dynamical system. So now for complex network like brain, they are comprised of very large number of interacting units. So one can ask the question that what is the effect of the coupling on extreme event and such system. So now we actually try to answer this question in the context of coupled neuronal maps. So here is the single neuronal map. This is the local dynamics of our coupled system. So it's a well-known K-Alvo map. It has two dynamical variable xn and yn. Xn is analogous to the action potential or membrane potential, and yn is the recovery variable, and there are 4 parameters, and this map actually captures many global dynamics of the neurons, and we have so it shows periodic nature, it shows chaotic nature, but here we are interested in the chaotic dynamics of this map. So now the question is that if I couple such intrinsically excitable system, so what would be the effect of this coupling on the extreme event? So now first let me show you the extreme event for a single neuronal map. So this is the time evolution of the action potential. So the black line here shows the average value of this data, and then the red line are the different cutoffs, and it shows that there are some events which are actually beyond the cutoff. There are several standard deviation away from the mean, and from the probability distribution we can see that it has long tail, and so the event has actually very less probability, they are actually rare. So we can consider it as a analogous to the extreme event. So now here what we have done, we have taken a ring of such on each side of the ring we defined such map, and then coupled them to different coupling scheme with different form and different range. So we have taken the diffusive form and the mean field, and we took two range. One is the local nearest neighbor coupling, and also the global mean field coupling. So this type of coupling actually this type of coupling is used in many coupled mapped system, and also this used in very to understand the many neuronal phenomena. So now I will show you the result for the extreme event on such coupled neuronal map. So this is the bifurcation diagram. So at a particular site of this coupled map, and so a red line here shows the cutoff, and so we see for the local, this panel shows the result for local diffusive coupling, and this shows the result for global mean field coupling. And we see there are, for a large range of coupling value, there are events in above this cutoff, and we have chosen these cutoffs for this work as 3 sigma away from the mean. Okay. So here in this case we see for very small range of coupling we see some events, and then as we increase the coupling the number of events gets lesser and lesser, and here we see the system goes to a spatio-temporal fixed point and the number of events is 0 here. So this is the time evolution of the action potential at a particular site for a coupling strength 0.2 for local diffusive coupling, and this is 0.02 for global diffusive coupling. And here black line actually denotes the average of the data, and red line denotes the cutoff. And we see there are events actually even in the coupled map, there are events in the above this cutoff. Okay, so there are for this 2 coupling scheme also there are extreme events. So now if I look at the written map of these values, we see that the action both the cases we see the values are actually chaotic. So that means they are actually uncorrelated, and so the events that are beyond the cutoff or above the cutoff, they are also uncorrelated. So we also looked at the spatial profile of this system, coupled system. So this is at a particular instant of time. We looked on the ring. So we see that this green line actually showing the average of the spatial profile, and the red line is showing the standard deviation x plus 3 sigma, which the standard deviation is the sigma is the standard deviation of the spatial profile. So now we see there are also events, there are different sites which are actually goes beyond the beyond the cutoff. So there are extreme event in different site also. So it has been seen for this and for both the cases. So this we call the extreme event in space. So now, so this is the probability distribution of the values at at particular site, and this the so this color our blue line blue curve is for the uncoupled case, and red and black for the two different coupling value. So it clearly shows that for the diffusive local diffusive coupling, the small value falls faster, and there are two regime the values actually falls in two different with the two different exponents. So it's clearly seen in the semi-log plot. It has two different slopes, and we see that if we increase the coupling strength also, there are the values are actually, the distribution has also long tail. So there are events above, actually above the cutoff or few standard deviation away from the cutoff. But for the local, for the global mean field coupling, what we have seen that as we increase the coupling strength, so the tails get shorter and shorter, and we see for higher coupling, I mean for 0.04, so here the values are actually bounded in a region, and so we can say that the extreme event are actually mitigated, or the large spike actually suppressed for this coupling scheme. So here I will show you the probability of extreme event in time for two again for two different coupling form. So PXE is estimated like this. So we count the number of events above the cutoff, and then we divide by this the total number sampled, and this data is shown for average over 20 initial condition, and the two colors are for two different system sizes. Okay. So here we see for local diffusive coupling, the probability of extreme event in time actually decreases for small value of coupling, and then it start increasing, and it saturates to a value which is higher than the value of the uncoupled case. So we see that the probability is actually enhanced for this coupling. And for the global mean field coupling, we see that it drops and then it goes to 0 here. So it's actually mitigated here. Now, so this is for the probability of extreme event in space. So here the PXE space is estimated like this. There are now total number of sites which shows the which has the value above the cutoff, and divided by the total number of sites that we have taken or we have considered. So here this data is also averaged over 10 to the power 4 time step and 20 initial condition. So now here also we see the probability of extreme events first decreases and then increases and saturates to a value which is higher than the uncoupled case. So in space also we see that the probability of extreme events is enhanced for this coupling, and here for the global mean field coupling we see that it drops to 0 as we increase the coupling strength. But if we see the bifurcation diagram, there we have seen that, so at 0.105 the system goes to a source of spatio-temporal fixed point. But here we have seen before that point also we see that there are coupling values where actually extreme event in space goes to 0. So to understand it in a better way, so what we have looked at, we looked at the synchronization error, which is defined as like this way. This is the standard deviation of the x values and averaged over time and initial condition. So we see that in the, so Z actually if Z is 0, it denotes the complete synchronization. If it's not 0, it denotes the desynchronized or partially synchronized state. So now we see that here Z is non-zero, but we see that there are no extreme events. So it says that Z greater 0 is not a so it's a necessary condition for non zero PXC space, but it's not a sufficient condition. So, but and also we see there is a small window of coupling where actually for some initial condition there are no extreme event in time, but there are extreme event in space. So, so we can say that so extreme event in space does not imply that extreme event in time. So now I will summarize my talk, this part of my talk, that our central finding is that the local diffusive coupling enhances the probability of extreme event in both space and time, whereas for global diffusive coupling mitigates the extreme event both space and time, and there is a small window of coupling where we actually see the where we do not see any temporal extreme event, but we see there are extreme event in space. So we also looked at another quantity, which is the inter-event interval. This is for local diffusive coupling. So this is for a weak coupling strength, and it's for a strong coupling strength. So so here we have seen that the inter-event interval actually does not show any correlation. So here the greatest cluster emerges around the small value of the inter-event interval. So that means there are extreme event in quick succession, and the longest interval is order of magnitude larger than the interval of this for the strongly coupled system. And so here, and also we see that the small inter-event interval can, how much time do I have? Over. Okay, I just quickly, I take 2 minutes just to quickly finish. So, and the long inter-event interval is very unlikely to followed by another long inter-event interval, and short inter-event interval can be followed by inter-event interval or any length. And here also we see that it's some noisy structure, and a broad cluster emerges around the inter-event interval 40, and so here we see some characteristics inter-event interval. So from here we can say that the so we can actually predict predict the extreme event if we know the previous events. So I looked at the another coupling form, which is actually diffusive in nature, but the range now we have increased from local to global. And here what we have seen that the probability of extreme event in time first decreases and then saturates to a value close to the uncoupled case, and for a long for a very large range of coupling strength we see the extreme event. But if I look at in the extreme event in space, there are no extreme events in space if for the coupling value greater 1, and we see that here Z is 0. That means we see the synchronous firing of neurons, the synchronous temporal extreme event, which actually has been seen in many in the neuronal system during the epileptic seizure. So this is the thing that this is the thing. So that we have seen the local diffusive coupling enhances the probability of extreme event, and we have also seen the extreme event in space, and if the extreme event in space does not imply the extreme event in time, and vice versa. And so the coupling form actually determines the which extreme event will develop in a system, and also we looked at the inter-event interval to gauge the short-term reassessment, and that's all. Okay. Thank you for your attention.
Thank you, Anupama. So there is a time for short, quick question. Yeah.
So please go to slide number 4. So I want to know what is your T-span length for the distribution.
Sorry, slide number 4.
Yes. It seems to be very short in my opinion. So
What?
what is the T-span length for this distribution plot?
What is the
T-span means what is the time interval you
time
took?
interval for this distribution? So we took just time interval. What do you mean that?
Means integration time. Integration
Sorry?
time. Okay, then what is? But in my opinion, this is not good enough. You means
Oh,
you mean
spike interval. Okay, okay. It's one. It's 10 to the power 3. We took the total time series over 10 to the power 3.
so. Are you sure if you increase the 10 to the power 4 or 5, the structure remains same?
Yeah, yeah. The structure remains same. So,
But I don't think so. Okay,
Maybe
thank
you
you.
can discuss also approach to her later. So if there is no further question, let's thank